Hi, my name is Owen Redwood, and this lecture is part of the Offensive Computer Security Open Courseware in 2015, hosted at hackallthethings.com. This lecture will continue the fuzzing lecture and cover some advanced topics. We're going to go over taint analysis, and by extension of that, dynamic taint analysis techniques and how it works in general. We're going to revisit code paths and their importance. We're going to introduce symbolic representations with an example and some advancements in all of these topics and hybrid techniques in the state of vulnerability research and bug hunting. So, hopefully you've done some fuzzing, and after a while you found some interesting crashes. And now you have to determine how exploitable these bugs may be, and which ones indeed are not exploitable. Essentially, determining what parts of the system you can corrupt with the given memory corruption vulnerability, if that's the case, is the task at hand. Hopefully, you can directly overwrite EIP and job is done. It's easy. But in other cases, it's more difficult to determine exactly how the memory corruption manifests and how user input directly influences the memory state of the process. In other words, the taint of the vulnerability.
So exploitability analysis, it's important to note that no accurate tools for automating this exist. This got cut off, but mono.py and bang exploitable, I believe, is a WinDebug extension. It reports whether it's definitely exploitable, probably exploitable, not exploitable, and then unknown is unable to make a determination. But it's not very accurate. Mono.py also has some exploit generation capabilities to automate the generation of a payload that would exploit the potential vulnerability. But in order to do this precisely, that's where taint analysis comes in. So the overall goal of taint analysis is to mark data originating from untrusted sources as tainted. So in general, all user input is marked as tainted because it could also be attacker input. And this can be done either statically or dynamically. And there are two types of dependencies that determine the taint of memory space: the data flow dependencies and control flow dependencies. There's also policies to consider when you're doing this. Do you just track one type or the other? And do you continue tracking things after they've been garbage collected or after they've been freed? Perhaps you'll miss use after free or use of uninitialized variables and vulnerabilities concerning those. Do you do your taint analysis at the bit level, or do you do it just at the byte level? The granularity may determine whether or not you're able to detect very subtle bugs. Obviously, if it requires bitwise precision, there might be some form of bit packing in the logic of the application. And so, essentially, what you're trying to do is that at the point of a crash, you want to analyze the state of the registers right when it's segfaulted or right when it's crashed, and perhaps right before it as well. If you see that all user data is in EIP, that's an extremely good sign that there's a vulnerability. And one way to do that is to pass it statically. The dumb way to do it is to pass it a very, very large pattern. Or pass it all A's, and you may see that EIP is 41414141. You could not access memory or invalid instruction at that address, hence the calls to segfault. But patterns allow you to not only identify that user input has been used in one of the registers, it allows you to identify precisely where in that user input the values of that input make it into the register. So, for instance, if you see that EIP has AD2A, all you have to do is search for in the string where AD2A is, And then in order to control EIP, you just replace AD2A with the memory address that you would prefer it to point to. And that's rather simple. So aside from that, there's various types of operations you have to keep aware of. There's maybe partial writes. Perhaps you only control the upper half of a register, or you only control 1 byte of a register, or perhaps you're able to control the whole thing and do a full write. Um, and then there's also operations like shifts and NAND. These are operations that just consume information, and for instance, shifts are irreversible, and information is completely consumed. So if you completely zero out a variable that has been used for user input, you should stop tracking taint at that moment, because then it's been overwritten by a static or constant value. And so you need to keep track of when a variable is assigned from an untainted object to in order to do the taint analysis precisely. Because false positives will lead to inaccurate reporting. And so patterns won't always work. Before we talk about that, we need to talk about endianness. If we haven't covered it already, endianness is extremely important. Whenever you're doing vulnerability analysis or just security in general, you have to start with the basics of the architecture, understand those, then understand the basics of the system, the operating system, and its memory model, its access controls, its basic permissions, and then perhaps past that, if there's a sandbox in the application, and what other security mechanisms may also be in place. So at the very basic level, at the processor level, the endianness definitely matters. And so, as I said earlier, if you straight see a recognizable pattern, it's probably a big endian system, because little endian systems like Intel processors and x86 specifically have little endian systems. So the following string AG1, AG2, AG would be represented in memory as AG, G2, 1A, AG, because the least significant byte gets placed first, and then it proceeds as following. And if you have any confusion over this, you should review this. It's a relatively simple computer science concept covered early in most curriculums, and you can refer to Wikipedia here. But absolutely, endianness matters and will determine whether or not you can pull off an exploit. So it's one of the simple things that have to be paid attention to. So, as I was saying earlier, patterns won't work in all applications. And the method usually fails if there's any transformation on the user input. For instance, if it's XORed with some mask or something like that. And this is just this dumb approach of throwing patterns at something. In any form of encoding and decoding or expansion, compression of user input, this is where patterns and simple analysis techniques will fail. So, as I was saying earlier, there's two types of dependencies. There's data flow dependencies and there's control flow. So data flow is effectively consider X coming from user input, and thus it is tainted, and say we statically assign Y to 2, and Z is the sum of X plus Y. Z is then marked as tainted because it is influenced by user input by a tainted source, but Y is not marked as tainted. It's rather straightforward. Now, control flow dependencies happen to occur when there's some sort of conditional statement that's evaluated, and it's evaluating a tainted source. For instance, consider X is tainted coming from user input, and there's an if statement, and this branch depends on the value of this tainted source. In this model, the control flow dependency, Y is considered tainted because it is influenced by a tainted source. This is also another important case to consider. So an instance where patterns wouldn't work and statically just assessing whether or not at the state of the crash there's user input in the register um, is any form of crypto, any form of encoding, any form of compression, any form of hashes. And this is also touching the realm of cryptanalysis and differential cryptanalysis. Um, and it's important to note that you're not going to be able to determine exactly when you change hello world and change the O here to an X, you're not going to be able to exactly determine with this dumb approach exactly what bytes are changed in the resulting hash. So the question is, how do you pull this off? How do you gain this level of introspection to the process? And that's where dynamic taint analysis steps in. Effectively, the approach is very similar. You tag all data originating from an unsafe source as tainted. You track the data during execution, step by step, and you identify and potentially prevent the unsafe usage of tainted data. And this, you should remember this, will probably end up on exam. So this usually requires some level of fine-grained control over the system. Perhaps the use of an emulator. QEMU is a fast x86. Also supports other architectures, emulator. And perhaps you only need a debugger. QEMU is used in honeypot research in the Argos framework to provide dynamic taint analysis as a honeypot. Effectively, honeypot is a system that has no production value, no value on it whatsoever, and it's just set up as a dumb target. Not dumb target. It's set up as a target. Any use of that system over the network is considered hostile. So in the realm of taint analysis, if you mark all activity coming in over the network as tainted, with QEMU, they basically emulate the operating system and have very fine-grained control, allowing you to see exactly when user data is being used to influence control flow. And in fact, it dumps memory of the target process, or rather the victim process, right away. At the moment that tainted user data is entered into EIP and controls where the processor begins executing, which is very, very interesting research and related to my own dissertation. Uh, Many targets are very complicated, and you have to advance your fuzzing capabilities to more evenly cover all the code paths. Because in reality, most code spends 90% of its time in loops, and perhaps a particular code path that contains a very, very critical vulnerability may only be, on average, executed less than 0.1% of the time. And your fuzzer, if it's not designed right, may never find it. So now that we've covered taint analysis and ability in theory and how it's done in practice to determine whether or not a vulnerability exists by exploring how things end up transforming in memory and how user input specifically taints regions of memory. Let's talk about code paths and talk about code coverage and these other topics, symbolic representation and differential fuzzing, come into play here. So it is important to cover interesting code paths. However, branches are expensive. If you start keeping track of all the paths you've taken through code, and code often contains many, many different branches, it becomes very expensive, and each branch imposes an exponential cost. So it's important to avoid loops, to avoid already covered paths, and this requires careful optimization and also the ability to reason about code. It is rather simple with the disassembler to detect all the branches in a binary. However, for instances of reverse engineering complicated things like malware, malware authors often go to great lengths to obfuscate how things are assembled and perhaps exploit tricks in various reverse engineering tools like IDA and debuggers like GDB to cause things to not disassemble correctly, um, which hopefully we'll cover a little bit in later this semester. So, like I said, in reality, 90% of your execution time is spent in loops, just in general. And this subject alone, optimizing this, has been subject to many dissertations. If you take computer architecture, you'll hear about this plenty. And the term branch prediction will come up a lot. And like I said, if your fuzzer produces tons and tons of cases but never produces really good vulnerabilities, it may be because it's not executing the more interesting code paths. So in order to get it to more evenly distribute the test cases among the binary, we're going to have to explore this. And this is where the realm of symbolic representation comes in, because this field allows you to reason about the code. In essence, it's kind of summarized by the statement, if this Boolean, does it really matter past this if we test 1, 2, 3, because clearly all values from 1 to 1599 are accepted. So do you need to spend 1,000 test cases evaluating this? So symbolic representation allows you to represent variables by symbols, and these symbols can take any value. And furthermore, you replace concrete operations with operations that just manipulate these symbolic values. X plus some constant C, or X plus some constant B. And by transferring it to more of an algebraic approach, you can have a special focus on branches. And obviously, branches go one of two ways. And this approach allows you to keep track of path constraints. So, in essence, when a program branches on a symbolic value, when doing symbolic representation, the system follows both branches at once, because it's just taking a symbolic approach. It may do this in parallel depending on how this algorithm is implemented. But what it does, first and foremost, is it keeps track of that path constraint that determines which path is going to be decided. So when an execution eventually ends or terminates, and it's determined that it crashed or perhaps there was a bug, it can then iterate through all the path constraints that it kept track of and determine quickly how to generate a test case to solve all of that. And this is the realm of constraint solvers, and if you pull this up on Wikipedia, you'll get a gigantic list of various constraint solvers for various different languages, and it's a very well explored field. So by reducing the challenge of covering code to an algebraic problem of following all the paths at once, obviously this imposes an exponential cost in memory, being able to store all of this. By being able to cover it all at once, perhaps you do it in parallel, you can find all the different ways to reach all the different paths in memory in a rather efficient manner. However, it depends on your computing power and the algorithm itself. As I said, each branch imposes a binary exponential cost, and this scales poorly, and a high number of branches lead to an explosion of code paths. The basic solution to these is using heuristics to cut out following uninteresting paths, and also to explore these possible paths in parallel. So that roughly ends that topic, but it's worth talking about intermediate representations because it's a very, very similar topic. And intermediate representations are kind of the mix between symbolic representation and reverse engineering. And often intermediate representations can be symbolic. They can be something that you can do all of this aforementioned stuff with. Um, or, on the other hand, it could be pseudocode that may not be able to be reasoned about and you may not be able to throw a constraint solver at. Intermediate representations, first and foremost, are just a front end for whatever you're trying to analyze that facilitates an easier analysis of it, of reverse engineering it. So, for instance, for a binary, just ones and zeros, an intermediate representation would just be the disassembly of it. That's rather simple. However, most people can't sit down and read assembly language all day, and so an intermediate representation for that would be a higher order language that perhaps is pseudocode that shows you roughly at a higher level what is going on. And that is precisely what an intermediate representation is. So this can be used for looking at machine code, it can be used for reasoning about source code, and it can also be used for reasoning about malware. So this is a rather difficult paper to get through, but if you're interested in this field, this paper is everything you wanted to know about dynamic taint analysis and forward symbolic execution, but might have been afraid to ask, but it's not an easy read for most people. To go over the gist of it, they present the simple intermediate language, which is perhaps not so simple, and effectively code is reasoned about by breaking it down into three aspects. First, a program is considered a sequence of numbered statements, and then the statements are assignments, assertions, jumps, and conditional jumps. So an assignment would be x equals 0. A conditional jump would be if x is less than 1, do this, otherwise go here. And likewise, conditional jump would be if this evaluates to true, do this, otherwise jump here. And an unconditional jump would simply be return, go back to the previous previous chunk of code. So, past that, expressions are reasoned about as things that have no side effects, things that do not change the program state, perhaps things that just print out the usage of the application and don't influence the control flow. So there are two types of operators. There are binary operators, and you see diamond B for binary and diamond U for unary operators. So x plus y. The x and the y are two values, hence the binary operator. And for x plus plus, it would just be one value, hence the unary operator if you didn't know this stuff already. So this also means address of, pointers, typecasts, use of size of, and stuff like that. For others, you might want to check out unary operators in the C family. And so don't confuse binary operators with bitwise operations like XOR and stuff like that. So this is getting complicated, I know, and I'm not going to require you to do this stuff. I'm just kind of explaining it at a high level. And effectively, the authors break down the language into these following operational semantics, which is not easy for most people. But so we have input. So for instance, like get character or get string from user input or over the socket. This is how it would be reasoned about symbolically. And then loading from perhaps hard drive, and then declaring a variable, a unary operator here, and a binary operator here. A constant being declared or used, Variable being assigned here, a unconditional jump. Um, I forget what T conditional, F conditional, store, and then assertion. So I'm just going to jump to the example. And this single line of code where it declares X to be 2 times whatever get user input is. It could be getting an integer or whatever. And simple, this evaluates to this giant symbolic representation, which is not so simple. Don't worry, this will not be on the exam. However, if you're able to break this down into this algebra, it's rather simple for the processor and the algorithm to reason about it all. Not so much for humans. So um, these approaches do definitely improve code coverage, but they're heavyweight and they're complicated and they might not always be worth it. That's the takeaway. So let's cover some recent papers as we finish up the first part of today's lecture. There's going to be another video split up covering exploit development because this will not take up the whole time. So adaptive random testing came out about a year ago. It's not state of the art, but it's widely cited, and if you're doing research in this area, it's something you should read. Effectively, back in 2004, they did research on how to distribute test cases more evenly in the testing space, and they demonstrated how it definitely outperforms just random testing, and it also talked a lot about constraints and the quality of constraints. We talked about this a little bit in the past lecture, and it accordingly described how to more evenly distribute test cases for more interesting constraints. And there's a really good discussion of it here on Embedded in Academia's blog. It's definitely worth reading if you're interested in this form of research. A paper that came out about 3 years ago proposed a approach that they use at VUPenn and was designed by VUPenn and Grenoble University researchers. And the paper's titled, A Taint-Based Approach for Smart Fuzzing. Effectively, it's a mix between taint analysis, using the taint analysis and heuristics to analyze how well you're covering the code in your fuzzer, and then adjusting your fuzzing appropriately. So it's differentially adjusting fuzzing to improve coverage based on taint analysis and heuristics. So it takes in vulnerability patterns, and obviously how good this algorithm is limited solely by how good your signatures are for vulnerabilities. Whether it's just looking at the machine code for stir copy and looking for wherever that might occur, because you might have just a blob of binary code with no symbols, no debugging information, and no function names, no variable names, just all binary code, and so that's what you may be limited to. So you take in vulnerability patterns, you do taint analysis, and then you generate test cases and execute them, and you adjust your test case generation based on how well you're covering the code. And then you check the outcome of the test case for various vulnerability properties, and you determine, or bug properties rather, such as a seg fault, and then you determine whether or not it's exploitable. That's the basic approach. It's a pretty simple read, worth your time. Now, another differential approach, or perhaps just smart and straightforward approach, is something called rocket-propelled chainsaw. Yes, security is fun, and we get to name things fun things. So this comes out of CERT, and effectively what it does is for Windows, when an application crashes, it asks if you want to send a crash report to Microsoft so they can pretty much ignore it and not help you fix that problem, which is what most people tend to think. Linux distributions are adopting the same thing. I'm pretty sure Apple operating systems have similar things too. Effectively, as an organization, what CERT has done with this project is they redirect these crash reports to their researchers, and they use these test cases as fuzzing seeds. And they mutate these test cases, and what they have is a wonderful engine for test cases that are already causing crashes, and the probability that a vulnerability can be found in the proximity of that test case is actually very, very high compared to other fuzzing approaches. So this obviously requires having access to a big organization that can have, monkeys on the keyboard causing all these crashes and not knowing how to, computer properly. That's how I say it. So rocket propelled chainsaw is pretty effective. It's pretty awesome. Another interesting development lately came out of Carnegie Mellon University Scilab and their application Mayhem, and the paper is Unleashing Mayhem on Binary Code. Effectively, at its core, Mayhem introduces a hybrid symbolic execution technique along with other testing techniques and fuzzing. And from what I understand, it is exceptionally good at finding very shallow bugs. And they tested it across the entire Debian repository for applications, testing hundreds of applications, and found 1,200 bugs, and decided to publish 29 of them as OJs. The other novel thing that Mayhem adds is that it also automates exploit generation. So it finds bugs and develops automatically an exploit for it, allowing you to pop a shell, which is dangerous if we were to get into the wild, I guess, which is why they don't release the source for that. But it was quite a event when they decided to just announce, hey, we've got more bugs than you can possibly handle. What do you guys want us to do with them? Because the average Linux tracker, I believe, is tracking thousands of bugs, 9,000, I believe, and 1,200 is more than any team could possibly handle in a week. So there's another paper worth talking about that, given a particular chunk of code in a binary, would use these techniques, dynamic taint analysis, and more so symbolic representation, to bubble back up to a tainted source and then generate a test case accordingly. Not all code paths are remotely accessible, or rather accessible to all tainted sources. For instance, if it's a server, you really wouldn't consider the initialization of the server where it's loading all of its local configuration files that the attacker doesn't have access to as something that would be interesting testing, which I believe Mayhem was able to catch a lot of those uninteresting bugs, and many of them had vulnerabilities automatically. However, in doing manual analysis of any form, you really wouldn't consider that interesting because you already have to hack the system and gain access to it in order to hack that application, that server, a service, which wouldn't give you anything further. And I can't unfortunately remember or find where this was, but if you're doing research in this area, it's something to consider as already being tackled. As for intermediate representation, there is the general decoder semantic language, I forget, toolkit. GDSL toolkit, it seems to offer a improved way of doing this and offers a great discussion on existing intermediate representation work and the pitfalls, and how most only can cover a subset of an instruction set, such as x86, And a lot of the work out there is duplication of efforts. And this is seeming to kind of coalesce all the findings in this field of work into a more cogent vision of what should be done. Um, so this is by no means a comprehensive coverage of the state of the art of fuzzing and stuff like that. So that's something I need to say.